In this next lesson, we will introduce the concept of power series. And to start, let's consider the following regular series. And you should be able to recognize this easily. If we expand a few terms, you should recognize this as a geometric series with a common ratio r. And what we know about geometric series is that when r, the absolute value of r is less than 1, then the series converges. And when the absolute value of r is greater than or equal to 1, then the series diverges. And what does that mean? So let's consider some values of r. And let's start with r equals 0. Then we'll do r equals 1/2 and so on. So when r is equal to 0, what is the series converges to? Because remember, it converges for all values of r between -1 and 1. So when r is equal to 0, we should be able to identify what it converges to. So it's going to be 1 plus 0 plus 0 squared plus 0 cubed, etc. So it looks like it converges to 1. Now when r equals to 1/2, we're going to get r plus 1/2 plus 1/4 plus 1/8 plus, and here we just need to remind ourselves that when geometric series converges, we know exactly what it converges to. It converges to 1 over 1 minus r. So when r is equal to 1/2, this series will converge to 1 over 1 minus 1/2, which is 2. Very similarly, we can find what the series converges to when r is equal to 3/4. That will be 4. We can try some negative numbers as well. It doesn't matter whether r is positive or negative, as long as the absolute value is less than the absolute value is less than 1, or the r itself is between -1 and 1. This formula works very well. And I guess it's worth reminding that when r equals 2, then this doesn't make sense, so we say it does not exist. So what do we want to notice here? We want to notice that this series, when written with some generic r, for different values of r, it gives you different outputs. So it is fair to say that this series behaves like what? Now let me remind you that earlier in calculus, or even not, we didn't have to go this far, but earlier sometime we learned that things that for certain inputs give us certain outputs, and when for every input there is only one output, then these things are called what? They're called functions. So it appears that this particular power series regular series, geometric series, behaves like a function. So, and it behaves kind of like this function, right? So, for which we produced this table of inputs, outputs, and for more inputs, we can definitely figure out more outputs. So the first observation, which is very important, is that when looking at a series with some generic common ratio, geometric series with some generic common ratio r, and it behaves like a function depending on different values of r. So it seems like here r is a plays the role of a variable, so we might as well just write that series with what we usually use as a variable instead of r. So for different values of x, this will produce different outputs, and therefore this behaves like some function. Which function though? How do we know which function does it behave as? And the answer is in the fact that we know that the geometric series converge to 1 over 1 minus r when they converge. So in our case, this what we used to call a geometric series, but instead of r, when we write x, it appears that it will act like this function. So this is what we have discovered, and we definitely want to make sense out of this. However, this expression at the top doesn't really make much sense yet, because we just never seen anything like that, and this is where the need for the introduction of power series comes in. We definitely need to define this object so we can start working with it. And we call this object, this new type of objects, we call it power series. So in general, a power series centered at 0 is something that looks like this. And we can actually start at 0 over here. And if we expand the first few terms, it's going to look like this. And this a n for different values of n are called the coefficients. And we can think of power series as infinite degree polynomials. If such thing existed, them and the power series will be the same thing. So that means we can inherit some of the vocabulary, such as calling those values coefficients, same way as we do it with polynomials. And here are some examples of power series. Here are some simple ones. This power series has all of its coefficient equal to 1. But of course it doesn't have to be the case. We can have power series as crazy as you may imagine. So again, this is not the craziest one, but something slightly different. and we can try to write out the formula. Looks like this is the formula, and the coefficients of this power series are powers of -1/2. So we may create different power series by changing those coefficients to be like anything, like literally anything. So what we learned right now from doing this exercise, let's summarize this. We learned that this, what we now know called power series, and it also acts like a function. Which function? So we again earlier discovered that it acts like this function. So this power series acts like this function, but it's not always true. It is only true when x is, remember x is your common ratio, so absolute value of x has to be less than 1. So absolute value of x being less than 1 means that x itself ranges between -1 and 1. So, and if this power series acts like a function on this interval, then you know how if it walks like a duck, sounds like a duck, then it must be a duck. So here's the same reasoning. If it acts like a function, it is probably because it is that function. So now that we know what type of object we're dealing with on the left hand side, we are more comfortable with putting an equal sign between these two. So what we're learning from this, again, as we continue to develop this, that we have series that live in their own world here. They may look like this, right? So it is a different series. And then we have the world of functions, which we're certainly more familiar with. And we may have some different functions here. And as of right now, we have a clear line between them as if there are two different worlds. But what we observing through this example is that some series are connected to some functions and vice versa, right? Some functions may be connected to some series. And this is exactly what we are going to study next. We're going to study these connections between series, which we would call power series, and functions. So naturally, there will be two directions in which we can ask a question. We can look at a power series centered at 0, and we can ask what function does this power series act like. Alternatively, we can look at a function and ask ourselves is there a power series that acts like this function? So these are the two types of questions that we will be interested in answering, and with that in mind we will be developing some theory. And before we continue, let's generalize the definition of a power series. So the power series doesn't have to be centered at 0. Power series in general looks like this. So if expanded, it will look like this, and we call this a power series centered at x equals c. For example, this series is centered at 2. And this series is centered at -3. So again, series, power series is an interesting topic, and power series are connected with functions, and we are interested in figuring out which functions are power series connected to, and whether we can take a function and find a power series that somehow acts like that function. In general, this is not an easy question, but when it comes to power series that are somehow related to the geometric series, then we can answer this question somewhat easily. So let's do the following example. Let's take this function and let's write this as a power series centered at 0. So how would we go about completing this task? Well, we are going to recognize that this is equal to this, and it doesn't matter whether we use X or any other letter. So if I use a star over here, then I will just use a star over there, but everything else is a part of this formula. So the goal is to be able to recognize, or if it doesn't exist, to create this pattern in the given function. And we're going to do that by algebraically manipulating the function. So with that in mind, let's take our function and let's take out the negative. And let's factor out 10 from the numerator and 2 from the denominator. And hopefully you'll see the pattern very soon. So when we take the 2 from the denominator, we have 13x over 2. And now this 13x over 2 is going to act as this star. And what does that mean? That means we can use this pattern to rewrite, and by the way, negative 10 over 2 is just negative 5. And we're going to use this pattern to rewrite the 1 over 1 minus 13x over 2 as sigma of negative 13x over 2 to the power n, and goes from 0 to infinity. And we did it. So we got this function. And we found a series that acts like this function. So let's bring the negative 5 inside. And let's separate that x from the inside of the parentheses. So we're going to have negative 13 over 2 to the power n times x to the power n. And the rest is just making it look good. Instead of negative 5, we're going to write 5 times negative 1. We're going to pull out the negative 1 to the power n. We're going to have 13 over 2 to the power n times x to the power n. So the final answer is 5 times, I guess let's write negative 1 first. So we have negative 1 to the power n plus 1 times 5 times 13 to the power n over 2 to the power n times x to the power n. And this is now a power series centered at 0, so we completed the task. Let's do another one. Let's actually take the same series, and this time let's, sorry, not the series but the function, and this time let's actually write it as a series, but let's center it elsewhere. So let's, for example, center it at negative 1. So that means we are going to write it in this form. So remember, the only tool we have is that 1 over 1 minus something is equal to this, of course, when the absolute value of that something is less than 1. Now, what we're going to do is we're going to start with this function, and we're going to create this pattern. And we have to have x plus 1. So if we want to have x plus 1 over here, the only way for us to do that is to have x plus 1 over here. And how do we get that done? Well, we are going to throw x plus 1 in here, but we don't just add 1 over there, right? Because there's a multiple of 13 in the front. We actually added 13, so if we want to keep things balanced out, we gotta subtract 13, and we still have that negative 2. So you can expand everything and you'll see that technically the expression is still the same. Now we're going to simplify it, and we're going to take out negative. So we're going to have 15 minus 13 x plus 1. And now we're going to take out negative 10 over 15. So we're going to have 1 in the numerator and 1 minus 13, 15 times x plus 1 in the denominator. And there's nothing we can do or need to do about the negative 10 over 15. I'm sorry, we can actually reduce that by 5, right? So negative 2/3. But the fraction now becomes the sum. This is our power series, so we take everything and raise it to the power n. So finally, so we can write it as a single fraction. And now we wrote the same function as a power series centered at -1. So again, it's important where the power series is centered, and as you could see, same function can be expressed as two different power series depending on where you center it. So next we will continue developing some theory, but again, remember the main goal is to answer these questions. This is our main goal. How to take a series and find the function that it acts like, and how to take a function and figure out what power series acts like that function.